Okay, we'll go ahead and get started here. Well, happy Friday, everybody. It's Friday of week 8, which means we just have 2 weeks of lecture remaining. Week 9, week 10, and then finals week, and you guys are on spring break and whatever. The last 2 weeks of our class will focus on randomization tests and bootstrap tests, which are very useful, very powerful uses of kind of the computer to answer statistical questions. However, so one of the prereqs for this class is Stats 10, or the equivalent of an introductory statistics class. But after teaching this class for many years, it has come to my awareness that many students, by the time they take this class, have either forgotten some key central concepts from Stats 10, or in high school they took AP Stats and maybe their AP Stats class wasn't as good, or I don't know, whatever, okay? So I think it's worth spending just a little bit of time in today's lecture to kind of review some key ideas from Stats 10, and so that's what we'll do here. And these are some key ideas that will play into what we do in randomization testing and bootstrap testing. Okay, so some key ideas from Stats 10. Generally, most statistics courses, at least our Stats 10 class, your first 3 chapters, they are on descriptive statistics. You talk about learning all of these descriptive things. The key ideas, though, okay, if I had to boil it down, is just the mean is important. That's gives you the idea of where the center is, right? And then the standard deviation is important. It tells you an idea of spread, right? And you should, if I said, explain to me variance and standard deviation, you should be able to tell me. Anybody want to give me a definition? Like, how do we calculate the variance? Okay. So the variance is kind of like the average squared distance from the mean, right? So you calculate the mean, you look at each individual observation, you look at its distance from the mean, you square that distance, okay? And you do this for all of them, and you kind of take the average, okay? The average square distance from the mean is the variance, and to get it back into not squares, you take the square root, and that's the standard deviation. So anyway, but it describes the spread, how spread out your numbers are, right? And so you spend some time talking about that. You do whatever, you spend like a few weeks just talking about the mean and the standard deviation. I love teaching Stats 10, okay? So I'm not knocking Stats 10 at all. I love teaching Stats 10, but really those first few weeks can be boiled down to these 2 sentences here, okay? Is that silly? And then you talk about the normal distribution, okay? And the normal distribution looks like this. And the key idea for the normal distribution can be boiled down to this sentence, which is if data follows the normal distribution, most of the values are near the middle, okay? That's it, okay? If it's unimodal and symmetric, you learn those terms and stuff. But the big idea is if it's normal, most of your values are going to be near the middle. Sometimes it's farther away, but almost always within most of the time within 2, most of the time within 1, okay? And almost always within 3, and only very rarely more than that, okay? So that's that, and you learn all of these, like using the normal table and all of that. You spend a bunch of time. And then there's this very important concept of the central limit theorem, okay? And the idea here is, this didn't render, but if we take a random sample of data from the population, we can take a random sample of data from the population, then we calculate the mean of that random sample, okay? And because the sample itself is random, if we were to take another random sample, we're going to get different values and a different sample mean. And we can repeat this a whole bunch of times, and each time we'll get a different sample mean. And it turns out that if you do this enough, if you keep track of all the different sample means you get from all these different random samples that we're repeatedly drawing from the population, all of those sample means themselves will follow the normal distribution, okay? Provided that your sample size is large enough, okay? And I think that's rather remarkable and impressive. And I just have a couple slides to kind of illustrate this. So here's our population, and these red lines down at the bottom represent a random sample of like 16 observations, and the mean of these 16 observations is right here. Okay, so we can see that it's a little bit different from the population mean, which is 0. It's a little bit right there. Here's another random sample, 16 observations. Its mean is right there. There's another random sample with the mean, another random sample, and I just did this a few times just to kind of give you an idea. And here I'm going to just run some code to build a sampling distribution. The code is only, what, 4 lines? So I just initialize sample means. This isn't even necessary. We could have just done it like this. And I just say, for I in 1 through 10,000, 10 to the 4th, I'm going to take a random sample of 16 using our norm. I'm going to store that random sample of 16 as our random sample. And then what I do is I calculate the mean of that random sample and store that into my vector in position I. Okay, and I do this 10,000 times. And so if I do that, and probably I should do this like 1,000,000 times or 100,000,000 times or something, but just so it runs quickly, I just did it 10,000 times. And we find the mean of this thing is very close to the population mean of 0. Okay, it's 0.003, and if I did it even more, it would be even closer to 0. And then the standard deviation of the population is 1, okay, because we're just drawing from the standard normal. And so the standard deviation of all of my sample means is around 0.25. It's 1 divided by the square root of n, which is what we've learned from the central limit theorem, right? You guys had to prove the central limit theorem in 100B? Derive it at least? Maybe? Okay, I got some people nodding their heads and some people shaking their heads, so. Well, you should. Okay, but anyway, so that's kind of, that's a very important idea, and it serves as kind of the foundation for all of our statistical inference, okay? Here's the histogram of our sample means. This looks normal, okay, and we can see that the spread is a lot smaller than the original thing. If we look at the QQ norm, it's a straight line indicating that it too is normal. So anyway, I don't know why any of these things didn't render. Okay. This is a wall of text. But the idea here is that we have now established that the sample mean of a random sample follows the normal distribution, okay? And that normal distribution is going to be centered at the population mean. And so this is going to form kind of the foundation for what we do in statistical inference in Stats 10, and that is, if we see a random sample and we see the mean of the random sample to be, you know, x bar, we can be confident that the population mean mu is nearby, because the central limit theorem says x bars come from a normal distribution. The normal distribution says most of your values are near the center, near the population mean mu. And so if we see this, we can be confident that it's probably close to the population mean mu. And so we can create a confidence interval that forms the idea for a confidence interval that because we know x bars are close to the mu, when we see an x bar, we can be confident that mu is close to x bar. Okay? And then conversely, when we do hypothesis testing, we start off and say, let's imagine some hypothetical population with these properties. You know, here's a hypothetical population, and this hypothetical population has a mean of 6 or whatever. And we ask, could this hypothetical population produce the sample of data that I have? All right? And that forms the basis of hypothesis testing. And And so we put that all together and we finally get to the t-test. And this is like week 10 of Stats 10, all right? It's 10 minutes into our lecture today. And, but this is, but I'm going to spend a lot of time talking about the t-test to just kind of review some of these foundational ideas, okay? And so for the t-test is, I don't know, maybe I can draw a little picture here. It says we're going to take samples from two populations, okay? So here is the idea of, here's pop 1, and here's population 2. And from population 1, we draw a random sample. And from population 2, we draw a random sample, okay? And this sample will produce X bar 1, and this sample produces X bar 2, okay? And we want to know if we observe X bar 1 versus X bar 2, what does that say about population 1's mu1 versus population 2's mu2, okay? That's what we're trying to answer, okay? And so the null hypothesis is going to be that there's no significant difference between the specified populations. Any difference is due to sampling error or experimental error. So we got mu1 is equal to mu2. That's going to be our null hypothesis, okay? And then the p-value is going to be the probability of obtaining a result equal to or more extreme than what was actually observed when the null hypothesis is true, okay? And when we talk about what was actually observed, we're talking about X bar 1 minus X bar 2. Okay, this is what we observed, and we want to know how extreme is that, okay? Anyway, just clear that out there, okay? And so when we take, if, again, if the idea is that the two populations are equal, all right? So if we have population 1 and population 2, okay, and we draw our samples, okay, what we would expect, if this one produces X bar 1 and we produce, this one produces X bar 2, we would expect X bar 1 minus X bar 2 to be close to 0, okay? Because the populations, if mu1 is equal to mu2, then random samples should have, you know, the random sample from population 1 should be close to mu1, and the random sample of population, random sample drawn from population 2 should also be close to that. We expect X bar 1 and X bar 2 to be somewhat close to 0, okay? And of course, because they're random, we're not going to get something exactly equal to 0. And so the question is our observed difference, okay, X bar 1 minus X bar 2, is that statistically significant, or is that significantly different from 0? Okay, and so I apologize. I don't know why my math symbols aren't rendering, okay? So here it says, what if X bar 1 is 10 and X bar 2 is 12? So we observe a difference of 2 points. And the question is that difference significant, okay? Well, you can't just look at 10 and 12 and say 2 points, that is significant or that is not significant, okay? The answer is that it's going to depend on the standard error. It's going to depend on kind of the variation that we see within our samples, okay? And so one possibility is that the standard error that we calculate from our samples is very small, okay? And in that case, that difference of 2, 12 minus 10, that difference of 2 is much larger than the standard error, and we would say that difference is significant. And on the other hand, it's also possible that the standard error is quite big, and so that difference of 2 is not much larger than the standard error, and we would say that difference is not significant. Okay, so these are just kind of rough guidelines, okay? again, sorry for the walls of text here, but as you review your notes, they can be helpful, right? So what we'll do is we'll calculate p-values, okay? And so p-values are probabilities. And basically, let me just kind of this is okay. So we observe x bar 1 minus x bar 2, okay? And there's actually, this value itself is a random variable, okay? And it comes from the quantity, okay? X bar 1 minus x bar 2 comes from basically a normal distribution or a t-distribution that's going to be centered at 0 and has basically a standard error equal to s1 squared over n1 plus s2 squared over n2. And if we observe a difference of 2, x bar 1 minus x bar 2 is equal to 2, the question is how what's the probability of getting something like 2 or something more extreme, okay? And depending on our alternative hypothesis, if the alternative hypothesis is mu1 is greater than mu2, then we would only shade in the area to the right, okay? But if the alternative hypothesis is that mu1 is not equal to mu2, then I'm just doing this very quickly, and I hope this is okay. We would shade in both sides because here a difference of 2 or more is interesting, but a difference of negative 2 or more is also interesting. Okay, so both the positive and negative sides are interesting to us. And this distribution, this is the distribution of possible x bar 1 and x bar minus x bar 2 values that I can get while the null hypothesis is true. This is our null distribution. Which states that basically this tells us what values of x bar 1 minus x bar 2 we should see if mu1 minus mu2 is equal to 0. Meaning if mu1 is equal to mu2, we should see x bar 1, x bar 2 to be centered around 0, but of course because of random chance they might be more or less. So this is our null distribution, and then the p-value is the probability of ending up in kind of these extreme zones under the null distribution. Okay, and so the scenarios are, if it turns out that the p-value is small, okay, so this is a lot to say. If our p-value is small, it means that our observed difference is so large that it is unlikely that these results were just because of random chance, right? And so we can be confident that our data is not just a result of random chance alone, but rather that the alternative hypothesis is true, okay? And on the other hand, if the p-value is large, it means that our observed difference could happen even when the only source of variation is random chance, okay? okay? It doesn't prove that the null hypothesis is true, but we have no reason to doubt the null hypothesis either, okay? So it's kind of like you know, I don't know. If somebody were to flip a coin, say 10 times, and it lands heads 7 times out of 10, okay, they would say, oh, 7 times out of 10, nobody would then say, this provides evidence that the coin is biased to flip heads more often, right? Because 7 times out of 10 could just happen quite a bit from random chance, okay? You got a proportion of 70% heads out of 10 coin flips, but that doesn't prove that your coin is somehow biased or favored to land heads more often, because that could happen by random chance. On the other hand, if somebody took a coin and they flipped it 10,000 times and they got 7,000 heads out of 10,000 flips, okay, that would provide strong evidence that the coin is somehow geared to land heads more often, okay? Because getting 7,000 heads out of 10,000 flips from a fair coin is almost impossible for that to happen just by random chance from a fair coin. So therefore, we come to the conclusion that our results is not from random chance, but rather indicates that our coin is somehow biased or something, okay? Okay, all of this stuff depends on what? It depends on the central limit theorem, okay? The central limit theorem says large random samples will follow a normal distribution, okay? But there were a few conditions, right? One was that the samples had to be large. Other was that the sample had to be kind of randomly sampled. There were a few other things like, and if your sample is not large, maybe you have to assume that the population is unimodal and symmetric, or at least sort of normal-ish looking, okay? And, you know, at the end of the day, it just depends on the fact that the central limit theorem holds, okay? Next week, we're going to look at randomization tests. We'll look at bootstrap tests, okay? And in that case, we are not going to rely on the central limit theorem anymore, okay? We're going to say, you know what, I'm not comfortable making all of these assumptions, saying that the central limit theorem still applies in this situation, and therefore I'm going to just do some testing here, okay? Our randomization tests, however, do require a different assumption, okay? And that is the assumption of exchangeability, all right? And so we'll just spend a few slides here to kind of just review some ideas of data collection, okay? And how do we collect data, at least in introstats?
Simple random.
Okay, so we often say our data comes from a simple random sample. Okay, so so that's one way, and that's usually for like an observational study. All right, and then what's the other kind of thing that we can get data from? An experiment, right? And what has to be true for an experiment? That we randomly assign the treatments, right? There's random assignment there, okay? All right, so we're gonna just talk about this thing over and over. We might get a little bit old here, but we're gonna talk about a few different scenarios, okay? And so suppose this is what we're gonna start off with, okay? We're gonna say, suppose a dentist wants to know if taking a daily dose of 500 milligrams of vitamin C will result in fewer canker sores in the mouth than taking no vitamin C, okay? This is what we want to know, and we've got a few scenarios for how we obtain data, okay? So we're going to say, so the dentist finds all the patients in the town within in the first 2 weeks in December to be subjects of a study. Okay, so they go through kind of their records and they say, all right, let's get everybody who had appointments in the first 2 weeks of December. We're gonna survey them, and then we ask them, you know, who takes 500 milligrams of vitamin C each day and who does not. Okay, and then we ask them, how many canker sores have you had in their mouth? And you check their kind of dental records to see if they've had any canker sores. And then we compare that group. We compare the proportion of those who take vitamin C and have canker sores to the proportion of those who do not take vitamin C but also have canker sores. And we're going to see if there's a difference between the proportions. And we do the math, and it turns out there is a statistically significant difference. Okay? What can we conclude? So, all right, so you're shaking your head and we're saying bad. Okay. So the answer is the patients are not a random sample from the population, right? How do we select them? We just got them by selecting them in the first 2 weeks in December. Okay, so they're not a random sample, so we cannot then generalize to the larger population. Okay, because maybe those who make appointments in December are different from the rest of the population. I don't know. Okay, the study is also observational in that we just said, do you take vitamin C? Yes or no or whatever, and no kind of cause and effect relationship can be made there. Okay, you know, at least not in this setup, because those who choose to take vitamin C may also have different habits than those who don't take vitamin C. Maybe they also have more vitamin B, and maybe it's vitamin B that's responsible for the canker sores. I don't know. Okay, maybe they are also more likely to brush their teeth. I don't know. Okay, so. So as far as this goes, all we can say is that for these patients, those who take vitamin C have fewer canker sores than those who don't, but we don't know why, and we don't know if this would be consistent with a larger group. Okay, so over here, we take all the patients with appointments in the first 2 weeks of December, and then we randomly assign, and we say, some of you will take vitamin C and some of you will not take vitamin C for 3 months. At the end of the study, we look at the proportion of who complained about canker sores and whatever. We find that there is a difference. Okay, what can we conclude now? Yeah, so here, because of the random assignment, we can make a cause and effect conclusion, okay? Because we said you are going to take vitamin C and you are not, we can say that the difference in canker sores is because of the treatment that we've assigned to them. Okay, we can at least draw some kind of relationship there. But again, this is not a random sample, so we cannot generalize to the population. Okay, and so all we can say is we don't know if this result would be consistent with another group. But we believe we know why, for this group, why the proportions differ, that it's because of the vitamin C, okay? All right, over here we just have the kind of the reverse scenario where we select a random sample of dental patients, convince them to take part of the study. We just do kind of the observational thing of seeing, you know, who takes vitamin C, who doesn't, and we observe some kind of conclusion there, okay? And so as far as this one goes, okay, because it is a random sample of dental patients in our town, we can infer that the results observed in this study would be consistent with the results of the whole population of dental patients. Okay, so because we drew from dental patients, we can at least generalize to all the dental patients in our town. And then if we then assume that our town is representative of the general population of all dental patients, maybe we can generalize to that group, okay? But we would be wary to generalize to anything other than dental patients, right? Because people who visit the dentist will generally have better oral care than those who don't visit the dentist at all. So, you know, and generally people who visit the dentist will, if you had to look at large swaths, will generally have more money than people who don't visit the dentist at all. There's all sorts of other things. So you wouldn't want to generalize to just the population at large, but all dental patients, maybe that's okay. Okay. But again, it's an observational study, so we cannot make cause and effect conclusions, right? So, you know, one of the big key ideas of intro stats is correlation is not causation and things like that. But we can kind of infer that those who take vitamin C will have fewer canker sores than those who don't, okay? All right, and then the last one, if we both get a random sample and we have random assignment, then we can do everything, right? We can generalize to the general population, and we can make a cause and effect conclusion. Okay? However, this scenario of getting a random sample and then randomly assigning is almost impossible in real life. Okay? The idea of getting a random sample and random assignment is not possible, at least not in a democratic society that values individual liberties, right? Because to participate in an experiment, we have to get patient consent, okay? And the very fact that not everybody will consent to participating in an experiment automatically no longer makes it a random sample, right? As soon as one person says, I don't want to participate, okay, which is going to be, you know, any random sample bigger than 10 or bigger than 2 probably, it's no longer random, okay? So this scenario is like nice to like fantasize about as a statistician, but it's not a reality, okay? Because yeah, again, once people start to say I don't consent to participate, it's not a random sample. Are you guys in 101B, or have you taken that already? Maybe did you have to do an experiment with like the island or something? Okay. Huh? Or observational study, right? You did experiments with the island and things like that, and you saw the island is purposely designed to be frustrating in obtaining your data, okay? And it's much, and that's like just a mini version of the frustration that a real research study, like you just had to click buttons on the computer. A real person has to like seek out people and have them fill out all of these legal disclosures and all of this stuff. And it's and then people will drop out in the middle of the study after you've spent like thousands of dollars collecting their first half of information, and then they say, never mind, I don't want to come in anymore, and you just wasted all of this time and energy. And anyway, the island gives you just a small taste of how annoying and tedious it can be for the life of a researcher. But anyway, this is nice. Generally, we can't get this. So we either have to deal with scenario 3, where we have a random sample and we do observations, or we get a sample that's not random because they've consented to join our experiment, but we do random assignment there, okay? And then we have to kind of jump through some hoops and say, well, this group of patients that consented to do our study might generalize to this larger group that we can then make inferences about over here. We might not be able to make cause and effect conclusions quite as easily, but there is something there. I want to point out that another professor at UCLA is oh, no internet. Okay. So UCLA, we have some really amazing professors, amazing research professors, and one of our guys is Judea Pearl. He works in the computer science department, and he wrote this book called the Book of Why. It's a little bit of a plug for him. I'm not getting any money or anything like this, but I do want to kind of just highlight the work that he's doing, and he's working on kind of this idea of cause and effect. Okay, and he's challenging kind of this statistical mantra of correlation is not causation, and his argument is that if you think properly about what cause and effect relationships do exist, you can draw cause and effect conclusions from observational studies, as long as you properly think about the relationships that exist in the data. And so anyway, fascinating book. I recommend it if you've got some spare time. And this is, just from our very own Judea Pearl in the computer science department. So that's worth considering. But as far as traditional statistics goes, the basic idea is observational studies, no cause and effect conclusion can be made, whereas random experiments, we can draw cause and effect conclusions. Okay, all of this will play into next week when we do the randomization test, which will require the use of the computer and all of that. Randomization tests, permutation tests, and then bootstrap. So we'll end a few minutes early today. We'll wrap up here. And those of you who are watching the video online, thanks for tuning in. And we'll see you guys on Monday.